the last one from 2025. And please note that we record these meetings, but it's the usual that we do. So today we are having a webinar on machine learning and optimization. And I would like to remind you that this is a forum from Europe, and that it's to provide a platform to support, empower, and encourage the participation of all genders in operational research within Europe. And that you know that we have different ways of doing so. So we basically recommend and highlight best practices to the Euro executive on issues women in OR face, that we try to promote championing networking and mentoring. And you can see that today's event is at the core of this objective. And then we also promote a conversation around how OR can be utilized to help create a diverse and inclusive future. So as I mentioned, we have this mentoring objective, and you can see here the Young Women for OR awardees from 2024-2025. And we celebrate today the webinar that around Yasmin, Marta, and Jasone, who are doctors at different countries. So Yasmin currently is in France, although moving to the Netherlands in next year. We have Marta located in Italy, and then we have Jasone located in Canada. So they will be giving a presentation about their current work, and we are very happy to have Professor Thibaut Vidal as our subject expert. So he works at the intersection between combinatorial optimization and trustworthy machine learning, with applications spanning transportation, supply chain management, resource allocation, and information processing. He holds the Scale AI chair in data-driven supply chains. And he's a professor at the Department of Mathematics and Industrial Engineering at the Polytechnique Montreal, Canada. So he is at the core, as I said, of the topic of this webinar. So what I would like to do now is to invite this first speaker. We will give each of the speakers 10 minutes, and then Thibaut will have questions for each of them. And for the audience, remember that time allowing, we will have a space also for a Q&A session. So I would like, without further ado, that Yasmin now shares her screen. And Yasmin, the floor is yours. Thank you so much for coming today.
Thank you very much, Dolores, for the very kind introduction. I hope you can all see my slides. So I'm Yasmin. I'm a postdoctoral researcher at ESSEC Business School in Paris, and my research interests are at the intersection of bilevel optimization and optimization under uncertainty. And this is also what this talk today will be about. So I want to share some insights about bilevel problems under uncertainty. And in particular, I want to highlight that the sources for uncertainty are much richer in bilevel optimization compared to classic single-level optimization that we are used to. So, but before we get there, let me first say a few words what bilevel optimization is and why we should care about it. So bilevel optimization problems, they are a powerful tool for modeling hierarchical interactions between two different decision makers, which we call the leader and the follower. Such hierarchical interactions arise in many practical applications, especially in the context of pricing, transportation, energy markets, or in security domains. Formally, these problems can be modeled by introducing a nested optimization problem in the constraints of another optimization problem. Here, the leader controls the variables x and the follower controls the variables y. Because of this nested structure, these bilevel problems are intrinsically hard to solve, even if all the problem data is exactly known. However, in practice, we often have to make decisions under uncertainty. In the classic single-level optimization setting, the only thing that can be uncertain in such an optimization problem is the problem's data. So uncertainty may affect the set X, capturing some variable bounds, for instance. It can affect the objective function f or some data in the constraints in G. The two main approaches to tackle such uncertainties in the literature is to use techniques from either stochastic or robust optimization. In bilevel optimization, of course, the data can still be uncertain, but now, because we have two different decision makers in a single model, data uncertainty can now affect both the upper and the lower level problem. Moreover, bilevel problems can also be subject to another source of uncertainty, which is due to its nature to combine two different decision makers in a single model. Namely, also the decisions or the observation of these decisions can be subject to uncertainty. So meaning that the variable vector x and y can be uncertain as well. And just as it is the case in single-level optimization, also in bilevel optimization, the two main approaches to tackle uncertainties are to use techniques from either stochastic or robust optimization. Nevertheless, to get a better understanding of the development of this field, we conducted a survey on this topic. And in the figure, you can see the number of papers that we cite in this survey per year. And what you can see from this figure is that over the last 20 years, there has been an increasing interest in bilevel problems under uncertainty. And regarding the contributions in this field, we also make two main observations. The first one is that the majority of the works deals with stochastic approaches to address uncertainty in bilevel optimization, but robust approaches remain scarce. And the second observation is that the majority of the works addresses data uncertainty, but there are only very few ones that address decision uncertainty. So therefore, I would like to shed some more light on decision uncertainty in bilevel optimization now, and to this end, we will consider one specific instance of decision uncertainty, which we call limited observability of the leader's decision. So an implicit assumption that we make in bilevel optimization is that the follower, so this is the Y player in this game, can perfectly observe the leader's decision X. But in many practical situations, especially in security contexts, this may not be the case. For instance, the leader's decision may only be partially visible, or there may be some observation noise, which is why the follower's observation of the variable vector x may be imperfect. Nevertheless, when the follower makes the decision, of course, it will be based on the perceived leader's decision, which may be different from the actual one. Of course, the follower can be perfectly aware that the information is incomplete, and in particular, the perceived or observed leader's decision can still provide some insight into the leader's scope of action. And this may as well be used by the follower when making his decision. And let me make this a bit more concrete now with one specific example on a security game, and which we model as a sequential bimatrix game. So these sequential bimatrix game, they often arise in the context of patrolling, and this is also what we want to consider now. So assume you have some security chief of a famous museum who wants to determine a randomized patrolling strategy for certain areas or wings of that museum. The objective of this security chief or the security staff in general is to minimize costs, which can include the costs for staff, for resources, but also the costs associated with lost or stolen stolen or lost art. The thief or a thief then observes the patrols and determines a strategy to rob the museum. Of course, robbery also involves certain costs, which may include the efforts that takes to enter the museum, but also the potential risk of detection. So overall, we consider a game with two players, the security chief and the thief, who act as the leader and the follower, and both want to minimize their respective costs. And formally, this can be captured by a so-called sequential bimatrix game, which takes this form in general. So assume now that there are only two areas or wings in the museum that should be patrolled. And in the table, you can now see the costs that are associated with patrolling these two areas. How you have to read this table: the first entry is the cost of the leader, so the cost of the security chief. And the second one is the cost of the follower, so the cost of the thief. In the deterministic setting here, so if we assume that the leader anticipates a follower who can perfectly observe the leader's decision, the security chief will be more frequently assigning patrols on Wing 2 or in Wing 2 of the museum compared to Wing 1. And in response to that, the follower will always try to attack Wing 1. However, the follower, so the thief, may be perfectly aware of some observation noise regarding the leader's decision and may thus want to hedge against erroneous observations. And this can, for instance, be done using a robust approach. So using a robust approach, the thief now considers a range of plausible patrolling strategies and hedges against the worst possible outcome, and this is modeled by the orange part here. The set U of X is the set of all plausible patrolling strategies considered by the follower, which are based on the perceived leader's decision X. And here we consider some interval around this perceived leader's decision, and we additionally assume that the follower is smart enough to anticipate a simplex structure of the patrolling strategy. The parameter p here controls the size of the interval. So meaning that for p equals 0, we have the deterministic setting as before. However, when we vary p, so when we hedge against limited observability using this robust approach, we can see that this can significantly impact the optimal strategies of the game. In particular, we can see that the leader's strategy can flip completely, so that Wing 1 is now more frequently patrolled compared to Wing 2. So overall, what we have seen in this very small and academic example is that accounting for decision uncertainty in bi-level optimization can significantly impact optimal solutions. And I guess I'm running out of time, so let me briefly wrap up this talk. So we have seen that bi-level problems include two decision makers who interact in a hierarchical way. And because of this nested structure, bi-level problems may be subject to two types of uncertainty, namely data and decision uncertainty. And if you want to learn more about limited observability and bi-level optimization in general, then please share and scan these QR codes. And anyway, thanks for listening.
Thank you so much, Yasmin, for keeping to your time limit. And thank you so much for showing us uncertainty into places So our next speaker is Marta Monaci. So Marta, would you like to share your slides?
Okay. Okay. 1 second.
Yes, and maybe you can make them full screen.
Oops. Sorry, 1 second. I am
Okay, thank you.
okay. I don't know how to. Okay.
Fantastic. So the floor is yours, Marta.
1 second, sorry. Okay. I want to remove the gallery view. I don't know. Okay. Now. Okay, now yeah,
Perfect. So
okay, now it's working, sorry. Okay, so hi everyone, and Dolores, thank you for the introduction. Today I will talk you about margin optimal trees for robust nonlinear regression. This is a part of an ongoing work together with Professor Palaggi and PhD student Ilaria Ciocci. In particular, in this work we focus on regression task. So we are giving a label training dataset composed of P samples, each with n input features, and a target label yi. So the aim of a machine learning model is to learn a mapping function able to accurately predict never seen data, so capable to generalize well on new instances. In particular, we focus on decision trees that are supervised learning methods for classification and regression. And indeed, they can model non-linear relationship while retaining the crucial property of being interpretable. Now, let's see how a regression tree method works. In particular, during the training phase, a regression tree builds up a binary tree structure of a maximum predefined depth, and it is composed of branch nodes in blue and of leaf node in green. And each branch node applies a splitting rule on the feature space, sending sample to the left or to the right branch. And usually the splitting rule is defined by an hyperplane function. And in particular, depending on the hyperplane splits involved in the tree, we can distinguish between univariate tree that involve axis-aligned hyperplanes or multivariate ones in which each hyperplane can select more than one single feature. Then each sample follows a unique path within the tree, reaching a leaf node, a terminal node of the tree, where the prediction is made by fitting a local linear regression model on the samples in the leaf. In this way, we obtain a tree that can be then used to predict out-of-sample data. Okay, it has been proven that constructing an optimal binary decision tree is a P-complete problem, and only recently, thanks to the advances in mixed integer programming, has been possible to address the optimal regression tree in a mixed integer framework. One of the first proposals in this direction was the one of Bersimas and Dunn that proposed a mixed integer model to build an optimal regression tree with linear hyperplanes in the leaves. Now we can finally introduce our proposal. In particular, we extend the margin optimal tree method called Margot that we propose in a recent work from classification to regression task. In particular, Margot for classification exploit the generalization capabilities of subtle vector machines using maximum margin hyperplanes at each node of the tree. So we extend this framework to regression by introducing Margot regression that, to the best of our knowledge, is the first optimal tree approach that uses the subtle vector regression paradigm within the tree. In particular, the aim was the one to inherit the generalization and robustness properties of SVRs, subtle vector regression, and this results in a novel mixed integer quadratic programming model for building multivariate optimal regression trees. So now let's briefly recall how a linear subtle vector regression works. In particular, given a dataset, the aim of a linear SVR is to find a prediction function that fits the training data with a given precision epsilon, forming the so-called epsilon cube around the hyperplane, as we can see in the figure. So in particular, SVR optimizes an epsilon insensitive loss, and this means that all the errors within the epsilon tube are not penalized in the objective function, making the model more robust to small noise and helping in preventing overfitting, while errors greater than epsilon are penalized using slack variable C and N. So, to find the best hyperplane coefficients, we have to solve this convex quadratic problem, where the objective function combines the maximization of the margin using L2 norm and the minimization of the prediction errors beyond the epsilon tube, penalized by the hyperparameter C. Okay, now we can introduce our margin optimal regression tree. Here we show an example of Margot regression with a depth of 2, and as in standard multivariate tree, at each branch node of our tree, the splitting rule is defined by a branching hyperplane. Instead, each leaf L employs a linear SVR to predict any sample xi that falls into that leaf by using a linear regression function. So we can introduce the variables of our model. In particular, for each branch node, we introduce variables WT and BT to define the splitting hyperplanes. And then for each leaf node, we introduce the SVR hyperplane coefficients WL and BL together with the corresponding slack variable CL and NL. So the objective function is simply obtained as the sum of the objective function of each single local SVR over all the leaf nodes. So the first term maximizes the margin of each prediction hyperplane, while the second term is a measure of the prediction error weighted by the penalty parameter C. Okay, now to give you a visual intuition on how Margot regression works, we tested it on a one-dimensional synthetic dataset, like you can see in the first figure, while in the second figure we represented the optimal Margot regression tree on this dataset. As you can see, the splitting hyperplanes are represented by dashed vertical lines, and samples are colored according to the leaf node they are assigned to. And each leaf, as you can see from the figure, fills a linear SVR hyperplane that is shown together with its epsilon tube in the figure. So this example allows us to understand why Margot performed non-linear regression. Indeed, the tree recursively partitions the feature space into disjoint region, and each final region corresponds to a leaf node that applies a linear SVR on the subset of samples that belong to that region, to that partition. Okay, now we have to model the path of the samples within the tree, and to do that we introduce the binary variable z for each leaf and for each sample xi to model the assignment of a sample to a leaf node or not. And just defining this variable for the leaf level allows us to derive the whole path of each sample within the tree. Now let's take a quick look at the constraints. First of all, we have to introduce the assignment constraints to force each sample to end up in one and only one leaf node. And then we have routing constraints for each branch node of our tree. The role of them is to ensure that the hyperplane splits are chosen accordingly to the leaf assignment of a sample. They are modeled through big M constraints, and in particular, if a sample is not assigned to a node, they are relaxed. Otherwise, they simplify to a set of disjunctive constraints to model if a sample follows the left or the right branch of the node. We can apply a similar logic also for the SVR constraints for each leaf node of our tree. And in this case, with an appropriate choice of the big M parameter, we have to model the fact that each prediction hyperplane in a leaf node has to be trained only on a subset of samples, the ones assigned to that leaf. This will be the resulting mixed integer quadratic formulation. Now I'm not going into mathematical details, but the main complexity of it lies in the fact that it crucially employs binary variable and big M constraints to track the routing of each sample within the tree, and this leads to a weak continuous relaxation. Now, let's move on to some preliminary computational results. We test Margot and the model ORT-LH from Bersimas on 15 dataset. In particular, we set a depth of 1, that means 2 leaf, and a time limit of 30 minutes. As predictive performance, we report the test R-square, and as optimization ones, we evaluate the mixed integer gap and the computational time. Okay, here we have all the results in detail. In particular, the best predictive performance are highlighted in color. We can see that Margot often achieves better predictive accuracy than ORT, sometimes with a clear improvement highlighted in bold. And also Margot certifies optimality in 6 instances, while ORT closes the gap in 2 cases. But however, as you can see, both approaches struggle to converge, reporting large optimality gaps in some instances. So, in conclusion, we can say that Margot method presents good prediction accuracy, and this thanks to the generalization properties inherited by the SVR approach. However, the major challenge in solving this problem comes from the presence of big M constraints and binary routing variables. This results in a weak continuous relaxation, leading to slow convergence and large optimality gaps. To address this challenge, we are currently investigating a tailored bandit-like decomposition algorithm to improve computational times. In addition, we have introduced symmetry breaking inequalities in the formulation to reduce equivalency matching solution, and we have also developed a warm start heuristic to initialize the solver. That's all, and thank you for your attention.
Thank you very much, Marta, for telling us about novel results on nonlinear regression. And then we move to the next presentation by Jasone. So maybe you would like to share your slides and see how it works. Okay, and then we make it full view.
Okay.
If maybe you want to have full screen use.
Let me. Okay. No?
Yeah, fantastic. Okay.
Perfect. Thank you so much, Dolores. So I'm going to present the work I'm doing with Professor Emma Friginger at Université de Montréal. And I'm going to talk about explanations for decisions under contextual stochastic problems that have endogenous uncertainty. So I'm going to focus on 3 things today. I'm going to, as I said, explain decisions for the first time that come from contextual stochastic optimization that have endogenous uncertainty, and I'm going to talk about what endogenous uncertainty is. I'm going to apply relative counterfactual explanations to these problems. We'll talk about that as well. And also that we found out that using Wasserstein distance as a regularization helps us with the computational runtimes. So first of all, a contextual stochastic optimization with endogenous uncertainty. We applied it, and I'm going to use this as an example, a competitive facility location problem. So in a competitive facility location problem, we have to decide a set of locations to open such that we maximize the expected demand. And this demand, the thing is, it's uncertain. And we have to try to predict this demand. So things we have some contextual features and information that are going to help us. This contextual feature can be the amenities that the location have, or maybe positive reviews that they have. And as I said, the problem comes that this demand follows a conditional distribution that depends on this feed of this information that I have, contextual information, but it depends also on the decisions that I'm making on which facilities I'm going to open. Let's see an example about this. So suppose we have the situation where we had 4 facilities and we decide to open 3 of them, facilities 1, 2, and 3. If there's like no contextual features, or they all have the same value on these contextual features, as facility 1, 2, and 3 are at the same distance from the user, the probability distribution of the demand would be a uniform distribution. It's but if there's some contextual feature, for example, that it's an attractive feature, have additional amenities or something like that, that facility 2 has, then this is going to affect the conditional distribution that I have, and it's going to it's going to be a higher probability to go for facility 2 than to go to facility 1 and 3. So this conditional distribution depends on the contextual features that I have. But it's also going to depend, obviously, on the decisions, because if I open facility 4, then the facility 4 is actually closer to the user, and it's going to have a higher probability to go there. And these decisions, basically what are going to affect is the support of the conditional distribution. So this is the kind of problem that we're going to work with. So we solve this problem, and then we go one step further. That is, okay, why do we need to explain the solutions that we're getting? So a lot of things now, like it happened that some algorithms that get developed, but they don't get adopted because we cannot explain the solutions. There's no transparency, and so it's important that not only we have good optimization algorithms, but we also get to explain the decision that we get. And one of the tools, there's a lot of different tools, but one of the tools is counterfactual explanations. So counterfactual explanations usually started appearing in the context of supervised classification, but we can also apply it to explain these kind of decisions in the sense of, okay, I want to know what is the change in the context that will lead to a change in a decision such that the decision complies with some new specific constraints that the stakeholder wants. Let's see an example. So suppose we had this same example as before, and we decide to open 1, 2, and 4. But facility 3 was in a specific district, and the stakeholder wants to know why was facility 3 not open, and how would I need the context to change in order for the decision to include this facility to be opened. So a counterfactual explanation would be, okay, if this contextual feature would be higher for like 0.1, then the solution would be to open 1, 2, and 3 instead of to open 4. So it's this new, so we're not saying this has to be the solution, but the solution complies with a specific constraints that I want. And I want to know which are the changes in the contextual features that will lead to that. This works on especially this last year. There's a lot of work now appearing in this sense in the counterfactual explanations in optimizations to explain decisions. We're going to differentiate between two works where there's no contextual information. It's just for linear optimization problems, where we can find some work specifically for the Kurtz et al. Work where they introduced the relative explanation. What are relative explanations? And then there's some other works on contextual optimization with exogenous uncertainty, where the uncertainty only depends on these contextual features. And also this work to calculate relative explanations. They just say this is the solution I want to obtain instead of just wanting the solutions to comply with specific constraints, but not deciding which is the new optimal solution. So in general, what we did was try to fill this gap. And what are relative counterfactual explanations? Relative counterfactual explanations is I'm not going to ask for this new solution for optimality, but I want the expected cost to not change too much. So giving a desired space that is the new constraints that the solution I want to comply, and relative explanations is this new context for which there is a feasible solution in this desired space that does change the expected code by at most an alpha factor. So for example, in the competitive facility location, I've captured a demand and I want to know the changes in the context to comply with these new constraints without changing the captured demand. About the conditional probability distribution, it can be there's no assumption on it, or it can be restricted to a known family of distributions. For example, we will apply this to what is the conditional distributions follows an MNL, a multinomial logit model. And I'm going to just share with you some ideas that we use to solve this. So for the cost function, that is how am I changing these contextual features, there's going to be two terms. One of them is just the dissimilarity term. I want the changes in the context to be small, for example, with the Euclidean norm or the L1 norm. And then we're going to add Wasserstein regularization. That is, I want the Wasserstein distance between the conditional probabilities. I want all these with the original probability distribution and the new one. Also, I want the changes to be smooth. And also introducing this regularization is going to help us with the computational times. And about what we know about the conditional distribution, even if we apply this to a problem where we know it's restricted to a family of probabilities, we can use the free version to compute lower bounds for our problem, which also helps us with the computational times. I'm just going to share some experiments to see this. So in the same problems before, we have 3, for example, facilities. If I solve these, facilities 1 and 2 are open. I wanted to know the changes in the context to open facility 3. So without regularization, there is going to say, okay, this is the contextual feature that you have to increase, and the probability distributions of the demands are going to change. If I introduce the Wasserstein regularization, I get other contextual changes, but the changes between the probability distributions are smaller. And then we solve this for the competitive facility location problem for different number of users, facilities, and the budget. And what we could see is when we put no regularization, we didn't put the Wasserstein distance, we often reach the time limit. But adding a moderate facility regularization reduced the runtimes sometimes by half of the time. Putting too much regularization does not help us too much. And surprisingly, we also found that putting this regularization, we got sparser solutions, explanations that is much more, it's better for us because it's saying you have to change these 2 contextual features and not these hundreds of contextual features, but just this small amount. And so basically putting this regularization, we get better results while keeping also relatively low the changes in the contextual features. And visually, just it's the same. When we put this no regularization, the runtimes, putting the Wasserstein regularization moderately help us a lot on the runtimes. If we put too much of it, it doesn't help that much. And this is the sparsity, it also reduces. But it increases sparsity, this is the number of the percentage of contextual features that are changing. So if it's smaller, it's more sparse. And also wanted to talk about it today. It's just trying to explain the decision. It's very hard, but can be done. As we have solved this for contextual stochastic problem with endogenous uncertainty, and especially we applied this to a competitive facility location under a multinomial logit model, and to solve this basically a mixed integer bilinear program. We want to go beyond MNL, apply it to other types of probability distributions, also apply it to other stochastic problems where maybe like assortment optimization and pricing. There's like a lot of work to do, I think. We've calculated relative counterfactuals where optimality is not wanted, but if we want to obviously also calculate weak counterfactuals, that is imposing that the new solution is actually optimal, we would get like bi-level problems that it's much harder, but I think very interesting to research and look for it. And you can find our preprint here. Thank you very much.
Thank you very much, Jasone, for this counterfactual presentation. So, Thibault, the floor is yours.
Yes, thank you so much, Dolores, and to all the presenters. I really liked a lot all these 3 presentations because they span very diverse topics. Bi-level optimization, contextual stochastic optimization, as well as the training of regression trees for classification. So this shows the tight connection between machine learning optimization and all the classical fields of OR, including like bi-level programming and stochastic optimization. On all this presentation were extremely interesting and very deep. So I have a lot of questions. I will try to stay relatively short to not overextend this seminar. So I will start with the presentation of Yasmin Beck about double the levels, double the trouble. So it's very interesting to see the application that has been used here with the example of the museum. I think it's very timely as in relation to the recent actualities. Is there other context of application in which you have tried to illustrate your concepts? For example, I think it's very interesting to study your problem in the case of interdiction games, where the leader would have a certain patrolling path and also maybe disclose other paths that he might take. How would this be applicable in this context? Have you considered this?
That's a very good question. Indeed, you're right that interdiction games are very interesting, especially in security contexts. I have worked a lot with interdiction games, but not from a decision uncertainty perspective, but rather from a data uncertainty perspective. So to answer the first question, I have not tried to apply the same techniques for limited observability on decision interdiction problems, which would be interesting now that you say it. Yeah, for us in this project, the focus was more really to capture these sequential bimatrix games, which here it was the museum example, which is quite timely, but it's actually applied in very many other security domains, especially in airport security. So I know that at LAX, they indeed have some kind of models where they have sequential bimatrix games in a stochastic setting to implement their patrolling strategies, and also for wildlife protection. So these are two main areas where these problems arise. But indeed, it would be interesting to study also interdiction problems with this kind of uncertainty.
Yeah, yeah, it looks very interesting as a research area at large. This links to very important concerns, I think. Another point about the formulation of the problem is that we assume the leader takes a certain decision, but the uncertainty that is connected to this decision is fixed, is a kind of fixed uncertainty parameter. It is not in the hands of the leader to create a distribution of possible decision. He takes a single decision on plus noise that is not in her control. Would it be relevant to study a variant of the problem in which the leader would be in control of the uncertainty levels, like he would himself decide on a distribution of solutions? So it would be like a bit a mixed strategy where he somehow publishes his probability distribution of decisions.
Good point. So you are referring, I guess, to some kind of decision-dependent uncertainty set if you're in the robust setting, or you can also take a stochastic perspective on this. Indeed, if the leader controls the decision, the uncertainty set, I think it wouldn't change too much in the modeling, because for us in the lower level problem or the followers problem, the decision of the leader is always fixed. So it would still be, from the followers perspective, a given set. But yeah, if, for instance, the follower himself can also influence the set by taking more efforts in observing the decision, I don't know, you have many possibilities, then it will make the problem significantly harder to solve. So especially because bilevel problems itself are already very challenging, and then if you put on top of this some kind of uncertainty modeling, this usually doesn't help in making these problems more tractable. So it really depends on the structure of the set, and we took a very specific structure so that we can still get tractable reformulations that we can give to some MILP solver. But indeed, it would be very interesting to find more generalizations of these sets, of course.
Yeah, that's really interesting. Also, I think if we keep a robust viewpoint of the follower and the leader is in control of the amount of uncertainty, I think the leader always would have an incentive to has as much uncertainty as possible, such that the robust follower has to hedge against a much larger uncertainty set. So maybe a robust approach in that case would not fit very well a framework where the leader is in control of the amount of uncertainty, you know?
Yeah, you're right. I mean, robust approaches are quite restrictive, and for many applications, this may not be the most ideal situation. So probably you would prefer some stochastic setting, or maybe some kind of distributionally robust setup, so that you get the best of both worlds, say. But yeah, so the whole field of bilevel problems under uncertainty is still rather new and in its infancy. So any kind of approaches or advances in this field would be much, much appreciated.
Yeah, well, looking forward for the next step because this was very interesting. Thank you so much for this
Thank you.
presentation. I will go with Marta's presentation. So it's very interesting what you did with the optimal regression trees. Since often in classification tree, we have greedy strategies for constructing classification trees that are very simple. Like you just split based on entropy or information gain criteria. And conceptually, it's pretty simple to understand. Training a regression tree, heuristically, it's a bit more complicated. It takes more effort to define a reasonable splitting rule, and making good heuristics is not straightforward at all. So before we delve into any global milk-based optimization method for that, I wanted to ask you if you have considered building heuristics as a baseline for your methodology.
Thank you for the observation. Yes, actually, we implemented some heuristics, so by our own, two kind of heuristic, a greedy one, so that is close to CAT, but employing SVR. So in particular, the branch node, we employ weakened SVR because the role of them is not to fit the data, but to partition the data. And at the leaf nodes, we employ a linear SVR on the subset of sample that we have greedy partitioned. Then we also develop another warm start heuristic in this case that was a mixed integer-based heuristic. So we train our Margot model, but we do some assumption on partition of points that have to fall together in the same leaf. And we use the approach, the proximity measure of a random forest. While considering, for example, CAT for regression, we didn't use it as a baseline because at the leaves, it doesn't fit a linear prediction, but it uses usually the mean of the target variable. So we can, of course, also benchmarking our model with CAT. Of course, CAT is quite immediate, very fast, but we didn't need it because maybe we thought it was too much failure because our model in the leaves was fitting a linear regression line and not a mean. So it has a more predictive power, of course, by doing this. On the other hand, of course, it's more complex and so on. I don't know if I I caught your observation. So we develop another heuristics to not to consider as a baseline, but to warm start our optimization procedure.
Okay, I see.
I
It's
don't know
very
if,
interesting. So
okay.
yeah,
If you know other
I see.
heuristics that we can use as baseline, they are of course welcoming.
Well, you could always look at every possible split and fit a linear regression on both sides to see what will be the loss,
Yeah,
and then take the best loss at each split. That would be better than taking the mean, but I guess it will be much more computationally intensive.
exactly. Yes, also for a heuristic approach. Yes, because
Yeah,
usually
that's
heuristic approach are univariate, no? So also in the branching hyperplane, they use one single feature per split. You use more feature per split, and on the leaves, we also train a linear regression line.
Yeah, and the mathematical programming allows to do that without any real overhead. You can get those diagonal splits almost for free. It's actually even perhaps a little easier to solve the models because it doesn't require restrictions that are binary on each splitting node. Yeah, that's super interesting. And when you compared the different loss functions on the leaves, so your study shows that it's better to use a support vector regression with this kind of shape of
Yes, like
loss.
a cosine, yes, a cosine shape function, a
Yeah,
sinusoidal.
yes, compared to kind of L1 or L2, that makes a big difference. Have you made sensitivity
Um,
analysis on data set to see that?
yes, actually, okay, we didn't compare with IL-1 because, of course, data set what was a highly nonlinear separable data set, no? So we can see at the first sight that one linear hyperplane doesn't fit very well all these nonlinear pattern, but we compare it with the schemas that are the leaves as a simple linear regression, L2 linear regression, and we can see on this, of course, this toy example, that SVRs are quite more robust in the sense that they are less sensible to outliers and they fit the data in a more, how can I say, in a more robust way. But of course, on this example, with one feature, we see some difference compared SVR compared to optimal trees with L2 regression, which because they minimize the squared of the errors. So all the points, also the farthest away, are weighted in the objective function with a square loss. While in our case, we didn't consider one inside, we consider only the one outside, and also we weight them with the xi variable, sorry, with the slack variable that is not squared, but it's epsilon xi times chi, where chi is the penalty parameter. So we give less importance to outliers. We can say this. Okay.
Yeah, I see how it is clearly more robust than L2 loss. That's well, I'm looking forward to see further work in this area. I had a very last final question for you. It was in relation to the sparsity parameters, because in your case you already have two parts of the objectives. You have one that concerns the width of the support vector regression, and one that is the classification accuracy. Another important parameter of the model in terms of simplicity is the number of split nodes. So that CMAS approaches on many decision tree algorithms, they impose some cost for each splitting node that is activated. Is it something you could also consider in your methodology?
Yes, this is a fundamental point, indeed, because we are looking for interpretability, and in particular, we employ branching hyperplanes and SVR that tends to select all the features available because they want to fit the hyperplane. So we propose another sparse version of Margot, but due to time constraints, I didn't tell about it, in which we introduce cardinality constraints. We prefer a hard approach and not a soft approach in objective function. We impose cardinality constraints on the number of features to use at each hyperplane, so we can explicitly control the complexity of each hyperplane split. So for example, we can say at this node you can select at most 3 features. In this way you improve the sparsity of the rules and also the interpretability. Because in the objective function, I think that, for example, Bersimas in the multivariate case minimize the number of features, not on the nodes, but of features in the multivariate case in the objective function, and while forcing them hardly for each branch node allow us to explicitly control each hyperplane, also to exploit more the hierarchical structure of the tree. So we use this approach, but unfortunately I didn't tell about it because I didn't have time. But it is a fundamental point, so thank you for the observation.
Oh, thank you. It goes in many interesting directions. Thank you so much for sharing all these insights with us. I have now last question for Jasone. So Jasone, you have done a crazy big amount of work on counterfactual explanations in a very complex, contextual, stochastic problem. One thing that I find very interesting in your work is that compared to earlier work, for example, of Alexandre Forel on quarters, you don't try to explain how we achieve a certain specific solution, but you try to explain how we get a solution that have a specific characteristic. So you are trying to explain decisions that are parts of a solution rather than solution themselves. Can you comment a bit more on this difference of methodological viewpoint and what it opens and what it permits?
Yeah, basically, the solution that we saw that as you said in counterfactuals from Forel and everything, it's just okay, what if a stakeholder wants to know how to obtain this specific solution, maybe because he knows or they know it's a normal or a specific solution, but I think usually when we're in a context, it's not that you want a specific solution, but there's some maybe fairness concerns or something external that you want to check. I will always see this in the facility location. Maybe it's not that you want to open this tree specific, but you want to make sure that one specific district has an hospital open or something like that. Or you want to, in a root problem, you want to specifically make sure or at least know what it needs to change to first go to this specific region or point. And in that way, you can explain the solutions without concentrating in just one solution, but it's on a spectrum of desired solutions that you want to reach, right? It's obviously more complicated because then you only constrain the space. And then when you are optimizing over what to change in the context, you also have to still optimize on the decisions. But I think it's really valuable and we have to reach for that. Yeah.
Yeah, that's very interesting.
Yeah.
As a part of sensitivity analysis, it's really
Yeah,
important.
true.
It's very fun because I think the field of optimization on OR has been doing sensitivity analysis for years, and we learn all about sensitivity analysis in classical LP scope
Yeah.
and other kind of models. But it's only more recently that with the rise of machine learning, all the explainability problems that they faced, that there is a renewed interest into also explaining optimization decisions and mixed predict and optimization decision. And it's very interesting to see that your work and other related work provide new methodological paths for doing that. So it's a very interesting field to check on.
Thank you.
Last thing I didn't fully grasp was the notion of weak counterfactual. So you said that in one case optimality is required, on the other is not.
Basically, now I'm saying I want to know what it needs to change in order for a new solution, that it has not to be optimal, but just that the cost that I obtain in the case of the facility location, the capture demand, that's not decreased, for example, of the original one that I obtained. With weak or strong counterfactuals, it's basically I want the new optimal solution to comply with these constraints, which basically it's a bi-level problem, which I don't know how to solve.
Yes, I remember. Yeah, you faced a bit the same issue with Forel et al.
Yeah.
Well, thank you. Again, that's excellent work. I don't want to overextend the question because we are reaching the end of the seminar, but I was impressed by all three presentations. It was very diverse. I want to thank you again. This was super interesting.
Thank you so much to
Thank
both.
you.
Thank you so much to the Young Women for War awardees. For the sake of time, I would like to share, say, my slides, which I hope they are being visible right now. So I would like to say that yes, there are more awardees coming soon for the 2025-2026. I would also like to say that we have a winter event coming up. So if you have your phones, please use this QR code to register. It's marvelous in my opinion because we reach out to different societies, and a couple of years ago we started to organize this joint winter event. And this year is even bigger because we have women in Africa joining us too. So it will be a lovely event, and it's always with a lot of activities. So I really would like to take a picture together. So if you would be happy to share your camera, I'm going to stop here, and I think we should be able to take a screenshot. So it would be lovely to have one of those with you. It's nice to see all of you. So I take one. Yeah, I'm in charge of the camera today. Yeah. So nice. Yeah. Thank you very much for coming today. It has been lovely. It's, as I said, the last one of the year. And then please remember to join us if you have the time in December.